All right, everyone, here we go. So yesterday's weekly assessment was it's not really the makeup test, but it's the pre-test. It was the first 9 questions of your pre-test. So I'm going to go over these, give you the answers, and give you some heads up on some things. So look, so on this one here, number one, the answer is B, because number one, they talk about a random sample. Automatically, when you see random sample, that means it's going to be a statistic. Has to be a statistic. So samples go with statistics. They both start with S's. So at that point, you're just looking for a number. And what number is it? It's 40%. So 40% is the statistic. Let's look at this next one. So sampling distribution of a statistic. So in other words, where do we keep all the statistics? Well, we keep them in a dot plot, and it can be a p hat or it could be x bar. It's that day we went over population distribution of samples and then a sampling distribution. So the sampling distribution is the distribution of values of the same sample size. So this sample size, let's say, is n equals 10, then all of these are x bars of a sample size of 10. It can't be a probability. It doesn't talk about randomization. It's not about variability. Differing means variability. So it's got to be C because we're talking about a distribution of values. Okay. This one, a distribution of values in a sample, that is just a single one of these by itself. So it's just a X bar by itself. That's why it won't be E. So let's talk about number 3. This one's a little tougher. It's the standard deviation of a sampling distribution. So the standard deviation of a sampling distribution is our sigma of p hat, or of this one would be x bar, right? Sigma of x bar is equal to the standard deviation over the square root of n. So we know that 0.08 equals the standard deviation over the square root of n. Well, n is 200. So we put 200 here, and now we solve for sigma, or the main standard deviation. And when we solve that, we get 0.08 times the square root of 200. And so now I know that my initial standard deviation is 1.13 based on this right here. And then I want to reduce this to 0.04. So I plug 0.04 in there. I put my 1.13 up here, and then I'm solving for the square root of n. So I just switch those two spots. If you want to do it the long way, it's square root of n times 0.04 equals 1.13. Then I divide both sides by 0.04. And when you do that, you get approximately 28.3. If you square that answer, because you got to square both sides, you may get 799 or so, but that's how you get the answer of 800. So this is a vocabulary-driven chapter, and it's bringing in a bunch of old stuff. So, which of the following districts has a mean that varies from sample to sample? The sampling distribution, which is this last one, this is mu of, let's say, p hat. That mean doesn't vary. It is solid. It's right in the middle. So the step before that is our distribution of sample data. It kind of, there we go. It kind of relates to like this question up here. So this is my distribution. This is my sampling distribution. We'll do that as 3. And this is my 2. And then my 1 is my population distribution. We'll just assume it's normal. So if it's normal, I automatically have a mu right in the middle. So what's the only one that it's going to vary? Well, it's going to be this one, because this is where I sample. Let's say it's a sample size of 10. I take n equals 10 out of here, and I drop it in here, and I find an x bar, or a p hat, let's say, because I'm talking about p hat. Then I take another, and I get a p hat, and another one, and I get a p hat. So these start bouncing around and round. It doesn't matter if it's p hat or mean. So this one right here is where the variance happens. This is why we take multiple samples of size 10 and we put them in a sampling distribution so we can find a mean that does not vary. That's kind of the idea behind that one. Number five, central limit theorem. Doesn't matter. Once you see the word central limit theorem, we're talking about large numbers greater than 30 that will make it normal. That's the key piece. Okay? So central limit theorem, doesn't matter if it's skewed right, skewed left. Once you do a large number of bulbs, it's going to make it close to normal. So that magic number is 30 is what we've been talking about. Last one over here, number 6, on the last page of the multiple choice. Number 6, this is on the formula sheet. Mu of p hat equals p, which means that this answer here is the same answer as that one. And then we just need to use our formula from the formula sheet to plug this in. Why is it not approximately normal? Well, this one fails immediately because 25 times 0.1 gives me 2.5, and that's not greater than 10, so it's false, so it cannot be normal. So that's just our conditions. Number 7, lots of words for a pretty straightforward question. Sample size is 500. Sample size is 500. Huge numbers here. Since the sample sizes are both 500, then Purdue and Indiana are going to be the same. Here's the reason why. Purdue is in Indiana. So one of the issues of not having geography class is the fact that you don't know that. So that's the idea. Since Purdue is in Indiana, they can be the same because of the same sample size. All right, so distribution supposed distribution of hair length for a high school, blah, 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 mean of 6.2 inches and a standard deviation of 5.8. So if we're looking at this, we're looking at selecting 10 students or 5 students or 1 student. So if we look at this piece right here and we get, it changes the standard deviation. So right now, if I select 1 student, they may be within 5.8 on either side. So they may be, so we've got 6.2 in the center. We'll just, I don't have a lot of room here. So we've got 6.2 in the center, and then to the left we got 5.8, and to the right we've got 5.8. If I select 1 student, that keeps this standard deviation the same by that equation. If I select 5 students, that gives me another value. And if I select 10 students, that gives me another value, and that square root of 10 here gives me like 1.98. So now if we randomly select 10 students, more than likely, because the standard deviation shrinks, those are the ones that will be within a mean value. Number 9 is just checking a bunch of different pieces when it comes to formulas. Remember, this formula is on the formula sheet. We need a z-score, stat minus parameter over standard deviation. My stat is always the one I'm looking for. That goes here. Greater than tells me it's greater than. 62 is the normally distributed mean. They give me the mean. That goes right here. And then don't forget we have sigma over square root of n. And since they give me 6 as a standard deviation, I divide it by the square root of n. And that's why my answer is there. All right. So let's tackle this stuff here on the back. So we're looking at the weight of eggs on a certain breed of hen, normally distributed with 65 grams and 5 grams. So you calculate the probability of a randomly selected egg between 62 and 68.75. So here again is my z-score, stat minus parameter by standard deviation. And so one of my statistics right here, which is my lower boundary, goes here. Here's the mean that they give me, and here is my standard deviation. A randomly selected egg, that's 1 egg. So this really doesn't apply because if I plug 1 in there, I'm still going to get 5. put my z-score in between, and this is my upper boundary. So this is my lower boundary. This is my upper boundary. So when they give you two data sets, this is what we're looking for. And this is the table version. So if you did normal CDF, it would be 62.5, comma 68.75, and then we'd put our mean and our standard deviation in right there, and that would punch out 0.4649. So then from there, we're using the fact that we took a sample of size 12. Well, we know that mu of x bar is equal to x bar, so we know that this doesn't change from up here on the top equation. But we do know, since I took a sample of 12, I have to put 5 divided by the square root of 12, and that gives me my new standard deviation, okay? So that is where they come up with this piece of information. Now from there, they turn around and they go, okay, well, I'm going to keep working with the same two numbers. So that means the setup is the same here. The only thing that changes is the fact that we took a sample and we have to do the standard deviation. So same calculation as we did up here, and we put it into normal CDF, except now my lower and upper boundary are the same, 62.5 and 68.75, but my mean is the same, but now my standard deviation I put in is 5 over the square root of 12, where up here it would have been 5. That's kind of the piece on those. Did you need to know the population distribution of egg whites was normal in order to complete? Yes, in both parts. Because the sample size wasn't large enough. The sample size was less than 30, so you can't use that central limit theorem. So we had to be told the population was normal. Okay? We were told it was normal. If we're not told it's normal, then we got to have a sample size of greater than 30. But since we were told it was normal, the sample size of 12 is okay. So that's how you answer that. All right. Last backside here, guys. So same type of problem. Calculate the probability of at least 60 out of 200 callers. So first of all, we're going to use this piece of information right here. So we have that piece of information, which is my mu of p hat, which tells me I have a p. My original one is 0.2, so that doesn't change. I do know from my formula that I got to use this piece of information to calculate my standard deviation. So I got 0.2 times 0.8 over the square root of 200, and that gives me my new standard deviation. Now from there, I've got to use what I'm looking for. Calculate the probability. This is going to be my stat. I sampled something. I sampled 200 callers and I got 60 out of 200. So I know my p hat is equal to 60 out of 200. Well, if I look at my statistic for z-score, it's statistic minus parameter. What they give you goes here. What you're testing, which that equals 0.3, goes right here. Stat minus parameter over standard deviation. Here's my standard deviation I calculated from right there. You can plug this in, or you put this in normal CDF. I'm doing at least, so that means it's a greater than, so that means 0.3 is my lower boundary. 0.3 is my lower boundary. My upper boundary is 999. And then my mean is what they give us, 0.2. And then I have a standard deviation of 0.028 that I plug in there, and that will give me approximately 0. Okay? Does it provide sufficient evidence to suggest that the proportion of male callers has increased from 20%? Explain. Yes, it does. It's nearly impossible to get a sample of at least 30. What's the percent chance of getting at least 0.30? 0. So there's very convincing evidence that the new host had an effect. Okay? because there's no chance of getting a 0.3. So definitely the new host had something to do with it. All right. So here we go. This is kind of one of those questions. Let's kind of break it down real quick as the last piece. We have a large population. We're good. Okay. Whom distribution is of the annual cost is slightly skewed to the left. So now we just got to think it's skewed to the left. What do I need at that point? Okay. So we've got skewed to the left. We take a random sample of 32. So if I'm skewed to the left, and I take a random sample of 32, all of a sudden now my sample is going to be normal because n is greater than or equal to 30. So we're working on that here, okay? So we took random samples of size 32, and then we took 50 samples. So we created a new dot plot. What did we create a new dot plot of? IQR. So these aren't just dots. Each dot is equal to IQR. Okay? So, briefly explain what the dot of 240 represents. The dot represents the interquartile range from one of the 50 samples. Just tells you right there. Below is a dot plot of the IQR from 50. So each dot is an IQR. Okay? Now, the last thing. Is the sample IQR an unbiased estimator of the population? An estimator. Remember, when we sample, we're taking this sample and we're estimating about the population. Estimating. So, we know that the 5-number summary of the true population is 380 minus 165. It appears that the distribution of the sample IQRs is slightly skewed to the right. So, they're talking about that this one may be slightly skewed, okay? But its median is 165, so it's safe to say that the center of the distribution is near 165. Therefore, the first quartile is an unbiased estimator, okay? It appears that it's slightly skewed, but what do we also know? That we can assume that this may be a normal population, so we can say it's pretty close to an unbiased estimator. Look at, if we just kind of look at that, that's pretty right in the middle right there. So that's why they come up with like 165. So this 165 compares well with the IQR of 165 up here. Remember, IQR is going to be 380 minus 215. All right, guys. So hopefully that helps. This is the one you got to really pay attention to. And we will talk to you later.